Hello everybody, I'm Massimo Pascale. I'm a fourth year graduate student here in Berkeley Astronomy. Today I want to talk to you about a project that I did last year called Unscrambling the Lens Galaxies in SMACS0723. The image here you're seeing is of the galaxy cluster SMACS0723, which was the first data from James Webb Space Telescope to be released to the public. And I was very lucky that it was something that was right up my alley. I'm very interested in these galaxy clusters, and specifically sort of these banana-shaped red objects that you can sort of see that spread out around the cluster. This is what we call a lens galaxy. It's been gravitationally lensed. And so I want to spend a little bit of time just covering some background about what this gravitational lensing is and what's really going on in that picture I just showed you. So in particular, we're located here at the Earth, and we look with our telescopes at these galaxy clusters that's kind of in the center, situated between us and then some distant, more distant galaxy. And so this galaxy cluster is extremely massive. We're talking orders of 10 to the 15 solar masses. And so all of the extreme gravity from that galaxy cluster bends, stretches, and shears the light of galaxies that are behind it. And so then when we look with our telescopes, we actually see sort of these sheared out images. So what you're seeing here is actually an even more distant galaxy that's situated sort of behind the galaxy cluster that's made up of all of these big white ellipses that you see. And something that's particularly interesting is that if you go through and you do all of the nitty-gritty math using Einstein's relativistic equations, you find that there's multiple solutions to where these images might appear. So in fact, if you have one single galaxy in the background, when it gets lensed and we look at it with our telescope, we see it stretched and sheared, as I mentioned before. We actually see it in multiple places. So what you're seeing here is a different galaxy cluster and sort of a pair of background galaxies. And you can see that pair appearing multiple times throughout the cluster. And so it makes for a very pretty picture, right? We can see all of these sort of background galaxies. But what's very interesting about gravitational lensing? And so there's kind of two things I want to focus on. One is that I mentioned it does get distorted. But when the distortion happens, it actually ends up magnifying that background galaxy. So these galaxies that you see here, we wouldn't be able to see without this gravitational lensing effect. They're just too faint and too far. So the magnification we get from these massive galaxy clusters through Einstein's relativity allows us to see galaxies we wouldn't before. So these galaxy clusters are in essence acting as natural telescopes out in space for us. Something else that's interesting is that by using sort of these sets of multiple images, right? So these sets of images that all correspond to the same background object, it gives us a lot of constraint on what's going on with all of the gravity, because the gravity is what's causing the lensing. And gravity is, of course, completely dependent on what the mass of the cluster is. So we can almost weigh these objects, these massive galaxy clusters in the sky, by using these lens galaxies as sort of our evidence. It's almost like if you see a footprint in the sand, trying to figure out how heavy that person must have been to create that footprint. And so what's particularly interesting about that is that we know that a lot of the matter that makes up everything in our universe is actually completely dark to our eyes. We call it dark matter. It doesn't interact, or at least for the most part doesn't interact with light at all. And we know very, very little about it. It's one of the greatest questions in science right now. What is this dark matter? And so by weighing the entire galaxy cluster, this gravitational lensing effect, it doesn't matter whether it's visible or dark. It's affected by both. So from that, we can actually estimate what the dark matter of these galaxy clusters might be. And that's going to eventually give us more insight into what this very mysterious substance in our universe that doesn't interact with light yet makes up 80% of all matter. And we can use that to get some insights. So in particular, we're going to be using this cluster, this SMACS0723, and the JWST data from it to sort of pick out these lens galaxies, or unscramble them, so to speak. And that's going to allow us to weigh what this galaxy cluster is. And it's particularly useful to use James Webb Space Telescope for it, because that telescope is much more sensitive. It's going to be able to see things that are even fainter and even further, meaning that we can pick out even more of these lens galaxies. As you can see, they're literally almost popping off the screen here. They're so bright, they're so red. They just really contrast the background greatly because of JWST. But let's take one step back behind JWST to HST, which prior to JWST going up last July, Hubble Space Telescope was sort of the premier way to do this type of science. And already you can see that the image is a lot more dull. This is the same one that I just showed you, except now with a slightly worse, but still state-of-the-art up until this year telescope, Hubble Space Telescope. And so this cluster had previously been analyzed in this way, where they sort of tried to pick out as many of those sets of lensed galaxies as they could, and try to weigh that cluster. But as you can see, they were really only able to pick out 5 sets. They're labeled up here, and so you can see it labels up to 5. And so using sort of the best available telescope data that you could get for this cluster prior to 2022, they were only able to pick out 5. And there was some other wide subset of data that they were able to use to get other evidence, and they found that the lensing mass, so the mass of this cluster, was around 10 to the 13 solar masses. And then what you're seeing is this curve here sort of maps out the expected distribution of that mass across it. Because not only do we know the total mass, we're actually able to map it out spatially. So then enters JWST, and you can already see sort of the stark contrast that you get from going from Hubble Space Telescope now to the most premier telescope, JWST. And you can see, like I mentioned before, the arcs literally popping off the screen. The amount of signal to noise we get is just wonderful. I don't think that there's a better comparison out right now to show just the raw, awesome power that we get from James Webb Space Telescope. And with that, we're able to identify a lot more than those 5 sets that previous groups have done. And so in particular, you can see some of the individual arcs. I've zoomed in, and you can see how faint and kind of dull it looks compared to now. Not only does it look much brighter, but you're actually able to pick out a lot more details. There's kind of all of these little compact little knots that you couldn't see before. So this is going to allow for a much, much more in-depth look at galaxies that are very, very far away from us. And so what we set out to do was to increase that number of 5 that they had before by finding as many sets of these multiple images as we possibly could. The reason being is that every single time you add in a new set of lensed galaxies into your constraints, you get even better estimates of what the mapping of the mass must be. So we're really trying to get as in-depth of an analysis of the mass distribution as we possibly can. And so what you're seeing here is I've sort of broken up the cluster into a couple of different images, and I've labeled every single one that we were able to pick out. And this is done sort of one by eye, because it's an image of the same galaxy, right? So you can kind of look at it in different parts of the cluster and say, oh, those look the same. And then also, we're able to use that sort of old analysis that was done by that previous group to vet these, because that analysis, while maybe not the most detailed or the most precise, is still fairly accurate. And so we should expect that if we find a new lensed galaxy, it should be consistent with what they found before. So overall, we ended up increasing it all the way up to 19 sets. So I mentioned before they had 5, and so we've now increased up to 19. This is, factor of 4 improvement in the number of constraints that we have to be able to map out the mass distribution. And so what did we end up finding? Well, we found a mass that was, in terms of the total mass, I would say very consistent with what they had found before. But of course, we were sharing 5 of those sets of lensed galaxies, so we don't expect the answer to change a ton in terms of maybe the total mass. But where I think that things get very interesting is that you can see I've now sort of mapped out a contour of constant mass here. And it's a lot more elongated compared to the one that we had before. So this one, I think, is still some degree of elongation, but it's a lot fatter. And then when we go here, we see that it's a lot more elongated. So why is this particularly interesting? Well, typically when we look at these galaxy clusters, we actually expect this to be more circular. The reason being is that these clusters form with many, many galaxies sort of all dynamically interacting, and eventually, when everything's said and done, and they've done interacting with each other, it should kind of situate such that the mass is mostly spherical. You don't usually expect to get this degree of elongation in the mass if the cluster is what we call virialized, or if it's very settled. Which means that we might actually be seeing a cluster in its formation. All of these galaxies still interacting with each other, maybe groups of galaxies merging into one large galaxy cluster. And so this could give us insight into the evolution of how galaxy clusters form in the first place. Another interesting way to sort of probe this scenario is to look at what we call the intracluster light. So, you look at this picture, which I have really, really stretched out, and you can sort of see the individual galaxies, but then you might notice that there's this sort of faint glow that seems to encompass the entire cluster. And this is due not only to the galaxy light sort of spilling out, but also because there are tons of stars and hot gas that sort of exist within the cluster, maybe not belonging to any individual galaxy, but because of all of the dynamics that is going on, where the galaxy gravity is pushing and pulling on each other, have sort of stripped stars off of these individual galaxies, and now they're sort of situated out within the cluster. And so if I map out sort of that curve of mass that I showed before, that sort of shows how the mass is elongated, and you compare it to this sort of stretched out image where you can see the intracluster light very well, you can see that the intracluster light seems to more or less follow that same degree of elongation. Now the intracluster, that's very interesting because people have postulated the intracluster light is usually well coupled to the dark matter, meaning that if you can tell what the overall shape of the intracluster light is, or the ICL, you might be able to tell what the shape of the dark matter is. And so that is, at this point, only a theory, but is further corroborated by what we're seeing here, where we saw that our mass distribution was elongated. And remember that mass distribution includes both the visible and the dark matter. And then we're looking at the intracluster light, and similarly elongated. And then both being elongated, once again, now points to that scenario where maybe we're seeing some ongoing galaxy cluster merger, and there's some dynamics that haven't quite settled here yet. In particular, if we look sort of at finer details in the intracluster light, you can notice that it doesn't look totally smooth. Over here, there's like a big cavity, and over here, there's a little bit of a smaller cavity, or maybe a lobe. This is also very unusual. Prior to JWST, I don't think we'd ever seen this in a galaxy cluster before, or at least not at this detail. And so that's particularly interesting because similar to how I said when a galaxy cluster is very settled, you expect sort of the mass to be very circular and smooth along with the intracluster light. You don't expect to see this high level of sort of structure in the intracluster light. Once again, pointing to the idea that maybe we're seeing sort of galaxy cluster formation in action rather than after the fact. So one last thing that I kind of wanted to go over is that there are these, I mentioned that this acts as a natural telescope, right? So I spent a lot of time focused on that dark matter aspect where we weigh the cluster. Now I want to focus on the fact that we now get a natural telescope out of this gravitational lensing. And in particular, I sort of want to point out what's called a fold image. So I mentioned that the objects, they get stretched and sheared, right? That's why you see them in these odd banana shapes. And they appear in multiple places in the cluster. And so there are certain images where it actually should fold along a line. So you imagine you see one half of the galaxy here, and then it gets reflected across this line, such that you should see the same galaxy kind of on both sides. And so if you look closely, you can start picking it out, right? I see this dot here, and I see the corresponding reflected dot over here, and same with this one. So when you look at these, as you get closer and closer to that center line, objects can become even more and more magnified. Such that when you get to these two blue dots here, which you can see sort of, they're the same object, but they've been reflected across this line, the magnifications for them start to go into the hundreds. Meaning that over here, maybe we're seeing some large region of a galaxy, but as we start to get closer and closer, we can probe smaller and smaller details. Maybe this blue object that we're seeing here is actually some compact cluster of stars, probing even further details. And then one last thing I want to point out about this is that, I think it's a little hard to see on the screen, but you can see sort of this red offset part to this blue knot. And I had just told you, right, that if something appears on one side, it should be reflected to the other side. And yet there's no red reflection right here. So this is a particular case of lensing where it's not just the whole cluster, but actually maybe an individual star in that intracluster light is passing in front and causing a little bit of extra magnification on just one side, such that while these objects might be magnified by, say, factors of 100, this individual little red dot here might be magnified by factors of thousands. Meaning that if before we were probing, maybe a cluster of many stars, perhaps here we're seeing an individual star in this galaxy that has just been magnified so much that you can see it right there. Now, I think that most astronomers in the room would be particularly skeptical of that little red pixel that I showed, because it's pretty difficult to make out any detail, and indeed, I was also very skeptical. But I think it becomes more obvious when you sort of look at all of the different images that we have in different filters. So each image sort of probes redder and redder objects. So as you get to sort of the image with the higher number, so from 090 all the way to 444, you expect that redder objects should appear brighter and brighter, and blue objects should appear sort of fainter and fainter. And so you see, sort of in this first image, I have marked with A and B those two knots that I had showed before, right? And so as we move to the redder images, those two knots become fainter and fainter and fainter, and eventually you're left with just one knot. And so it's hard to see because of all of this background, right? But if I subtract it off, I think it's much clearer when you look at these insets. Where here you have sort of the two blue knots, and I've marked the position of the upper knot with this plus sign, right? And then when you go to this part, not only does that object with the plus sign drop out, but it actually seems to get brighter right here. And that must be that red object that we're seeing. It's not the blue one corresponding to A, because if B suddenly disappears, A has to disappear as well. Because remember, it's reflected across that line. And so instead, we're seeing some very special lensing event where we're perhaps seeing an individual star. So what can we conclude from all of this? I think that considering that this was, the first data to be released with JWST, it's a great start, right? There's going to be many, many programs, there already have been since this work was done, to look at more and more galaxy clusters and potentially weighing more of these and getting more insights into how galaxy clusters evolve and how dark matter might work. Additionally, because of this sort of natural telescope effect and the idea that James Webb Space Telescope can see even fainter objects than we could ever see before, we might be able to probe these very distant galaxies to greater levels than ever before, similar to how we were able to maybe see that individual red star. And finally, I think that probing sort of what we're seeing in the ICL, this sort of unprecedented structure that was there in the intercluster light that we had basically never seen in galaxy clusters before, I think this will continue to sort of be a forefront for research in galaxy clusters. Thank you.